بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so welcome to the lecture number 5, and probably this is the most important lecture in this course. It's like the meat of all the things that we learned, and we're going to learn about the language modeling. It's about transformer, and we all know that transformer has made a complete revolution in artificial intelligence substantially. It's basically the core technology for what we know currently as generative AI and large language models. And in this lecture, I'm going to go into all the very particular details about the concept of self-attention and how it is built. So originally, I thought I'm going to provide the whole transformer large language model in one lecture, but I'm going to divide it in 2 lectures because I want to show you all the details about how self-attention works, okay? Also in terms of calculations, and later on we're going to build over this to see how a large language model like ChatGPT was built, and also other representational architecture like BERT have taken benefit from transformer technology. So if you remember, so far we have talked about feed-forward networks as one possible way of language modeling, like for example word2vec to provide one vector representation with some semantic information. This is basically the question of the last midterm about the evolution of language modeling, and then it went through recurrent neural network for sequential data processing, so we can capture a relationship into a sequence, especially that a sentence is a sequence of words. So with recurrent neural network, every output will depend on the current word and all the previous word, okay, in some of the ways. But RNN has some issues like the vanishing gradient problem, and it cannot capture long-term dependencies. So LSTM has come as an improvement of recurrent network by adding the concept of long short-term memory that capture better the long-range dependencies to some extent and to a certain window. But still it suffers also from the other common problem, especially we cannot do parallel processing, and it doesn't have a full understanding of the whole context, although it is much better than recurrent neural network. And this is what actually motivated the need for transformer. And yes, okay, yeah, so this slide summarizes better the evolution of language modeling. As already mentioned, with feed-forward neural network, we have fixed input size, okay, and fixed input windows, predicting the next tokens or creating embedding models. There is no sequential dependencies, and there is poor context understanding because the concept of sequence doesn't exist into feed-forward networks. Now, recurrent neural network, as already explained, there is the concept of hidden state that will carry information from the context, from the previous information, and it has the ability also to process variable length sequences. And this helps actually to process all natural language processing information, but it has the problem of vanishing gradient and limit the long-range dependencies. LSTM was proposed as an alternative or an improvement of recurrent neural network by adding the concept of gates, the forget gate, the cell gate, okay, to carry out information from the past and augment the information. So we have long-term memory and we have short-term memory that will both carry information, which reduce the problem of vanishing gradient, but to some extent, because the sequential also, there is a problem of limited parallelization. We cannot process the sequence in parallel. This is why it's slow in both training and also in inference. So transformer is basically getting back to feed-forward network, but we change the way on how to do the feature extraction. Okay, in feed-forward network, we have hidden layers that can do some feature extractions. In computer vision, we have convolution neural network that can also make feature extraction. But in transformer, we have the concept of self-attention. This is actually the new technique in transformer. In terms of how we extract feature extraction is to pay attention to the relationship and the dependencies between the different tokens or the different words inside the same context. And this context can be a text, or it can be an image, or it can be a voice, or anything else. Of course, transformer doesn't come without any limitation. We're going to go in details about the complexity, the quadratic complexity of the self-attention technique in the sequence length. And the idea here is that we have a feature extractor with self-attention that will extract the relationship between the different words or tokens in the context, and finally provide a prediction model. Okay, so why transformer? Of course, we have already enumerated the different problems with previous architectures like RNN and LSTM, the issue of parallel processing. Okay, so in transformer, we can process all the different words all together or tokens. However, here it's purely sequential. We have also the problem of long-range connections. Okay, so this is RNN and LSTM. They still have to go through the word one by word. Of course, LSTM is a little bit better because we can carry more information from the past, but still, you know, when you have very long sequence, even the information that you have carried along the long-term memory, you're going to forget it in some of the ways. Okay, even if you have an excellent memory, you cannot remember everything. There is always part of the memory, things that is not really recurrent, okay, as for example, like rare events or rare words. Maybe with LSTM, we can forget about them quickly. Also, we have the problem of context handling. RNN and LSTM use fixed length hidden state to summarize the past information. While in transformer, we have the concept of dynamic attention. So don't worry if you don't get all the information about attention, because we'll dive deeper into all these concepts. This is just an introduction. Okay, so this is the general architecture which I'm going to present. Other limitation also, we have the memory bottleneck. Okay, memory scaling with sequence length. The hidden state for each step create a high memory usage. This is why we cannot process very long sequences. The problem also, it's in the transformer, but there are some techniques that actually alleviated the issue. Okay, because also the self-attention, they can scale more efficiency across larger batches. There is also the problem with LSTM RNN of capturing complex relationship, especially in very long context, and also the exposure bias. Okay, so what is a transformer architecture? This is the general architecture as we already introduced it before. You start from an input text, then you will do tokenization, the classical way of segmenting the word into tokens. There are different techniques like BPE, sentence piece, and the different things that we have introduced. And then we will do the embedding. Of course, we will discuss later in detail that we need to also encode the position of the words with the embedding of the tokens, because if we don't do that, we're going to lose the sequence or the order of the words into the sentence. And we all know that the order of the words into a sentence make a lot of sense. If you make any exchange, we're going to lose the semantic. So it's really important that we both encode the position and also the embedding all together to provide not only the semantic information, but also the position of the word into the sentence. And then this is now the new thing. It's the transformer block. This is where the features will be extracted. What does it mean, features? Is the relationship between the tokens. Okay, this is what it's all about. This is not new. It's basically a feed-forward network that is going to take the input from the self-attention. But the all magic happens in this block, which is called the self-attention. And this is basically the focus of today's lecture. And you know, depending on the type of the architecture, at the end, you're going to generate also either probability of the next token. If, for example, we are in a generative language model like ChatGPT, we're going to have what is the probability of the next word. For example, al-fa'ru yuhibbu akl. It can be, for example, bread with 5%, food with 10%, cheese with 85%. So by learning the semantics between the relationship between the words in this block, we are able to predict to a good extent what could be possibly the next word with some probability. So looking at it from another perspective, from an abstraction perspective, we will start from a tokenizer to divide the words into different tokens. Then we will have embedding, and then this is what we have inside a self-attention module. We will have several transformer blocks, and the transformer block will contain two sub-blocks, self-attention and feed-forward network. And this is going to repeat several times depending on the number of layers. And this is what makes the size of the model. مثلا يقول لك ChatGPT it has 175 billion parameters. Okay, it has several layers. Every layer it encodes some weights. The weight, for example, is encoded over 32 bits, well, 16 bits, well, 8 bits. So all these parameters will play a role into the overall size, okay, number of parameters, and also the effective size in bytes. For example, if you have 170 billion parameters, if the parameter is encoded in 8 bits, it will have smaller size than if it is encoded on 16 bits or encoded on 32 bits. And this is why in the inference, usually we have recourse to techniques called quantization. So, for example, we usually train at 16 floating point precision, but later on when we want to do inference to reduce the size and the memory, we're going to quantize. What does it mean quantize? Changing the precision from 16 to 8 bits, and it went even to 1 bit quantization of the transformer technology to reduce the memory requirement and also the computation requirement. Yes?
Does it affect the accuracy of the model?
Yes, for sure. But of course, quantization techniques are made in such a way you have more benefit in the inference time more than degradation of accuracy. It still keeps the accuracy to a good extent. Okay. Okay, so looking at the generation process, how we do generate tokens. Does it make sense, everything I'm saying? If I go fast, please interrupt me and ask questions. So look now. So basically, imagine that you have a question answering system. So for the model, it's going to start from these green tokens, explain shortly deep learning model dot. So the model was trained in such a way that it can understand this context, and then we'll try to infer the next token. So at each iteration, it's going to take the current context and append the next token to it. Now, the new context will become this one. Then it's going to take this whole context and predict the next token, deep learning. So we're going to take this one. And this is what happens. Every time we're going to have a context, and it will go through the generative large language model. Of course, we have some limitation about how many tokens we can have as a context. This is what we call the context window. If we exceed the context window, the model is not able to generate, and this is why sometimes if you send a very long text to ChatGPT, say this is outside of the context window because it was trained on a certain amount of tokens to be processed at the same time. So if we give a certain amount of tokens, it will be able to apply self-attention mechanisms, which are matrices with certain dimensions that does not exceed 512. Okay, and at the end, going through different transformation, the role is to predict the next token, for example, uses. And here we have a context length or a context window of size 9, so we still have the ability to generate more tokens. So it's basically, we can say it's a regression problem. And this is why we call this model are called autoregressive. Regression because we will try to predict a floating number. Okay, we don't have classes, so it's a continuous space. Call it regression. And it's autoregressive because there is no labeling. So the model is going to learn from itself. In the pre-training phase, we're going to input a text, and from the text, we're going to learn the relationship. There is no manual labeling. And this is why these models are called autoregressive models. And we have two types of transformer architecture, two general types. We have generative model, like the GPT, generative pre-trained transformers, which are decoder only. And we have representation models, like BERT. So BERT, it's not, so it uses self-attention as feature extraction, but at the end, it's not going to predict the next token. It's going to give you an embedding of each token. So this is similar to what we did in Word2Vec. we give an embedding based on semantic, how close the words are close to, the meaning of the word are close to each other. Like in here, using the transformer technology, we have much better semantic capturing because we're going to learn the semantic from the whole context, not just from the previous two words or the next two words. So the context length here with the self-attention will play a role to find much better way of semantics. So BERT is one of the milestone works in encoding the word representation in a much meaningful way. And it's based on the use of the transformer technology. So here the output is different, the same feature structure. مثل ما تعملوا الآن في classification, you can have feature extraction with convolution. Then in classification you have a softmax function that tells you the probability of the class. In object detection we have a classification and we have a regression. Classification tells you what are the object, their classes, and the regression tells you the position of the object, so we can play with the output. But the whole magic is here. It's how to encode, so the how to extract the features. So the representation model, they are called encoder architecture. And generative model are called decoder only architecture. Why? لأنه at the end, this is going to start from a text and it will result into embeddings. So it's like it's going to encode this text into embeddings. This is why we call it encoders. And this is going to start from a text and will output a text. So it's going actually, it will have some kind of feature extraction here, but at the end it's going to return a text. So it will decode the features into a text. And we call them, so most of the generative model like ChatGPT, Llama models, DeepSeek or whatever, they are all decoder only architecture. And representation model are mostly to generate embedding, to have bidirectional representation, contextual representation of the tokens. And they have also, they use special tokens in order to specify the start of the sentence, the end of the sentence in the representational, on the contextual representation. So this is how generative model works. As already mentioned, we start from tokens, we convert them into embeddings, they will go into the decoder architecture, and finally they will predict the next word, the next token. For the representational model, so it's based on determining what is the missing word into a sentence. It's like filling in the blank here. For example, we can specify the word I and llamas, and here try to identify the missing word. Of course, because BERT, now this is like the BERT architecture. BERT, it has the ability to find the semantic relationship or the contextual relationship between the different tokens. So here it will be able to infer or to encode. The output here is going to be an embedding. And from this embedding, we will find the most likely word that is the closest to that embedding. Okay, so this is the difference. So here is going to input an embedding, and here is going to input a probability. واضح فرق between transformer decoders. So this is basically a probability of the next word. And here it will input the embedding of the missing word. And this is why we call it transformer encoder. Okay. So now we have a sentence. We made tokenization, and we would like to make embedding. But as already mentioned, in transformer we need to have positional encoding or positional embedding to also maintain the order of the words into the context. So there is a need for positional encoding in transformer because it requires an explicit position information and how it is implemented. Because so transformer, it processes all the tokens simultaneously. So if we don't tell explicitly what is the position of its token, you know, it's not going to make any difference. Look here. Imagine that you don't make any position information. At the end, what it will do, the self-attention, it will just make relationship between the words. So if I consider these words as just the word embedding, you know, there is no difference between making this word in any order. It will result, if you provide them in any order, it will always result into the same self-attention map. إذا embedding فقط يعتمد على الكلمة. self-attention, it will just make the relationship between every word and all other words. So given that the position information is not there, if I put the words in any order, it will result always to the same attention map. So this is the big problem. لأنه self attention هو فقط يعتمد على الآن لو فرضنا ناخذ dog chased cat نفس self attention نفس feature extraction here and here. لكن إذا نغير embedding of the word with another information اللي هي embedding of the position, so in this case doing the self attention in this order will be completely different of doing the self attention into any other order. So this is why we need to have the word order encoded or embedded into the word vector representation. Okay, so later on any correlation between the word will be affected by their position into the sentence. Okay. So to summarize, transformer process all the words simultaneously instead of sequential like in RNN. So in RNN we don't need to have any explicit position encoding because it's going to process the word into their order. So the order is native to the processing. Okay, it's implicit. Like in here, the lack of inherent sense of word order when you have a full context. لأنه transformer is like feed-forward network, putting everything together. So I need to have, it's crucial for the to explicitly mention the positional encoding. And look what we do, very simple. You have the token embeddings, and then you will find anyway, there are many ways on how to encode positions, and then make the sum together. This is called position-aware embedding. It's an embedding of the tokens that is aware of its position within a sentence. Okay, so we're going to learn both the embedding of the word and its position into the sentence. And there are two different types, what we call encoding and embedding. So in a nutshell, we'll see this in detail. Encoding, it's just a fixed static pattern of position representation. Well, embedding, it's learnable. So we don't provide anything in advance. We're going to learn from the corpus that we will use for the training. So this is the first position encoding that was proposed in the paper, Attention is All You Need. Okay, so the paper considered a context length of 512, and every position, so if you see, this is the token number 1 in the context. We will add this vector. This is a vector. Okay, this is a vector, yeah, we have 512 tokens, and this is a vector that we will add it to each position encoding. And this vector is represented with this formula. Okay, so the encoding of a position will be the sign of the pose divided by 10,000. It's a very complicated formula, okay, which will lead to a certain sine and cosine pattern, and it will depend on whether the position is even or odd. Okay, but this is one of the ways. Later on, you know, this is probably no longer used. There are so many other techniques that are used to encode the positions. Especially now, we rely more and more on embedding models because they are able to learn from the corpus. So we don't give any prior judgment about the position of the word within the corpus. And this is how we implemented in Python. Okay, this is the Python implementation. It depends on the sequence length and also on the dimension of the model. This is the dimension of the model, and this is the position this is the dimension of the model here. So the dimension of the model, it means every word on how many embeddings. So for example here, I think it's 128. So in the first paper, attention is all you need. We have a context length of 512, and we have an embedding vector of 128. Okay, because at every index, this is a positional embedding that will be added to the embedding vector of the token. واضح? So it will have an impact, okay, on the token information. Okay, so BERT, they used learned embedding, and this makes sense. لأنه encoding سنزيدو with the position encoding, it was used in text translation. أول paper, it was for machine translation, to translate from English to German. BERT, it's because it requires to find the relationship, the contextual relationship between the words. They have used learned embedding to learned embedding, so it's learnable. There is no prior formula like this one. And this is going to give waves, different type of waves that will be encoded into the model. Okay, so what is the advantage of using the sine and cosine? First of all, it's going to give you a unique value for each position within the context. It will help to capture patterns. It has already some very special pattern that will add some additional information to the embedding, to the token embedding. So the function will create repeating wave-like structure, making it easier for the model to learn relative positions. And also it allows extrapolation because, for example, if you extend the context length from 512 to 1024, you can reuse. So unlike learned embedding, sequential encoding works even for sequences longer than those seen during the training by extrapolating the same. But this could have some negative effect, because if we use, for example, the same position at token 0 at token 512, so in very long context, this could be confusing later on for the model to make inference. Extrapolation, يعني نفس embedding, we can extrapolate it for longer sequences. When 512 for 1024, for example. So this is possible, but this can make a confusion, because at the end we will have the same position embedding for token 0 and token 512. This could be an issue. So the pros and cons. So the advantages, there is an emphasis on the relative position, given the cyclic pattern. Okay, so can highlight the importance of relative position in the sequence, making it easier for the model to understand the relationship between tokens that are at similar distances from each other. It can extend to longer sequences, as we already discussed, and there is no additional parameters, so very simple to implement. It doesn't add any weight to the model. Actually learnable. Now, learnable embedding, you're going to add additional weight. I'm sure it will be part of the model size. Okay. So the cons, non-learnable encoding are fixed and doesn't adjust based on the task. So they will not depend on the corpus. Okay. They have potential inaccuracy for extended sequences due to the confusion of the position if we repeat the same cycle for longer sequences. And it has a fixed frequency spectrum. So this table actually summarizes the difference between positional encoding and positional embedding. As I already mentioned, the positional encoding is fixed mathematical function to encode positions. And here we learn the position embedding using the training like word embedding, like we did with word2vec. So this can generalize to longer sequences not seen in the training, and this one will be limited to the position seen during the training and will struggle with longer sequences because it's already learned this embedding based on a certain context length defined in advance. For the computation, there is no learning required, so it has less computation overhead. However, this is going to add trainable parameters, so the computation will be more intensive and will increase the model complexity. For interpretability, it's easier to interpret due to its structured periodic nature, and this is completely non-predictable because it's learnable. It's going to depend from many hyperparameters, from the corpus, from the size of the model, so it's less interpretable. For the memory efficiency, this doesn't add any trainable parameters, and this will require additional memory to store the trainable parameters. And this one was proposed in transformers in the original Vasvani paper in 2017, and this one was proposed in BERT and other advanced transformers. GPT, T5, they use learned embedding. And now it's more common to use learned embedding to have better accuracy than positional encoding. Okay. So as already introduced, the learnable position embedding, they learn position from the corpus, and each position get a trainable vector. So we will have a tensor. Okay, we start from like random variables of the embedding vectors, and then they will adjust vector during the training, and finally they will add to the word embedding. So this position embedding will be learned, and they will be added to the word embedding. So they are flexible. They can adapt to different tasks and data sets. This is why they are used now in GPT, because GPT can be fine-tuned on different type of tasks like text summarization or machine translation or writing codes. It's optimized for performance, especially it will give more accuracy, but it cannot generalize to longer sequences and require additional parameters because it will increase the model size. So these are different type of approaches proposed for positional embedding, like the absolute position embedding. This will assign a unique learnable vector to each position in a sequence. There is the relative position embedding, focuses on relative distances between words rather than the absolute position. And when you do the embedding, there are different ways on how you can add them to the token embedding. So the simplest way is to add any position embedding into into the token embedding, and this method is simple, effective for tasks with absolute word order is crucial. This one, it will focus on relative distances between the word rather than the absolute position. It will pay attention to this word is located at which distance, how many words will come after or will come before within a certain context. And the rotary position embedding, it utilizes rotational transformation to encode both absolute and relative position. So this is actually combines both techniques to have better understanding of the position of the words. Okay? So this is an illustration of the three techniques. So how it works, each position in the sequence is assigned a learnable vector, okay, that will be added to the token vector, and these vectors are fixed after training, okay, meaning that the same position always get the same encoding. مثل ما عندنا الآن. So after we train, the position encoding will be just for every position. كم عندي 512, every position will have a fixed vector. مثل ما عندنا في الساين and cosine, لكن the only difference is these are trained, okay, from the corpus. So the relative position embedding, So instead of assigning a unique vector at each position, we will compute the distance between words. Okay? So the position embedding will be relative to the position of each word with respect to the others rather than an absolute position. The model learns the relative position, not the absolute position. Okay? Which is different. Of course, this will depend on the loss function that we will apply to learn this position embedding. And these relative distances help capture contextual relationship. أنه العلاقات بين الكلمات غالبا it depends on the distance. If it is just next to it, مثلا لما نقول Saudi Arabia, it's always almost one distance. Okay? في بعض الكلمات يمكن يكونوا most likely to have second relative position ولا third relative position. So this is just like identifying the position either to an absolute frame or to a relative frame with respect to the word itself or with respect to the start of the sentence and the end of the sentence. And the rotary, it will make a combination of both. So try to capture as, let's say, global position and local position. Okay. إذا اشتغلت في ال transformation frame in space, so a position is represented for space either as absolute position or the relative position. Now my absolute position in the world, it depends on my GPS coordinate. And the relative position of Dr. Muhammad is maybe 2 meters away from me. Okay. And basically it will result at exact the same position, but the position it depends on the reference frame. So here, for the absolute position, the reference frame is the start of the context because it will be an absolute position. And in the relative position, it will be with respect to the token itself. Okay. And the combination of both, it will take both of the best of both worlds because we will capture the absolute, the global information and the local information, the contextual understanding. So you can see the evolution even of the transformer on these very simple details. It will make big difference into the performance. And the objective is always try to model the language. How can we find the best contextual relationship into any language? That's the biggest challenge. So all these evolutions is try to have the best possible representation. And this is a table that will summarize the key differences. So you have it here as a reference. So the absolute is used in BERT, Albert, so APA BERT, it uses absolute. RPET5 transformer XL, it uses relative, and GPT-4 and Llama, of course, the most sophisticated, they use the last technique using positional embedding, and it works well for every long text and large-scale LLMs, NLP tasks. They adopt this rotary approach. Okay, now we're going to stop for Maghrib prayer because this requires a full attention. It's about the self-attention. This is like now the biggest part that we'll introduce later, inshallah. Any question? Yes?
Relative position, relative to what?
Relative to the token itself.
So each token relative to the other token?
Yes. مثلا نقول كلمة هذه, it will have a relative position of 2 words with respect to itself. Okay. Yes. So of course the embedding is learnable. فمع الcorpus is going to understand مثلا إذا جت الكلمة هذه, what's likely after 2 tokens or 3 tokens, what's likely the words that will come afterwards. Okay. Yes. Any other question? Okay, that's fine. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, now let's get started with the very important topic about the self-attention. And good that many of you have already made the 2 certificates of deeplearning.ai. It's very good because it presents complex things in simple words. Of course, it's superficial with what we do, but if you understand this, you will easily understand what I'm going to present over here. So the concept of self-attention is based on a very important concept that is called query, key, and value. And to be honest, this is not a very intuitive concept. It's quite tricky, but I'm going to explain it in simple ways to understand how it works. And this concept is not actually part of, it's not new to self-attention. It's part from an older context that is called information retrieval. And they borrow this approach, and they have implemented in transformer in the context of self-attention to be able to capture the relationship. So let me introduce how this was used before in information retrieval. Imagine that you want to search a YouTube video. So you'll basically write your query or your question, and this is now what we call the query, which is related to this word. Okay, it's a query, something we need to look for. And you will search into a very large amount of information, okay, which is basically the database of information that we have. And this whole database is actually our value, okay? And from all this database, you will select the best results, okay? What does it mean, the best results? The results that are the more relevant to the query. So we will find the results based on their keys, okay? And this is what we call here a key. We will find through this query what are the keys that matches, that have the most relevance to this query. And finally, we will have a relevance score. For example, here, attention, demystifying attention in computer vision convolution neural network. Okay, there is attention here though, so this looks like high relevance. Now, this is another one, smaller relevance. This is completely different, very small relevance. So this is how the information retrieval works. We will have a query that we need to retrieve. We will have a value that is the whole bunch of information. And we will find the keys that are sorted according to their relevance to the query. This is the same example. So this is the value. It's the whole bunch of videos, for example, that you have on YouTube. And we will identify the most, for example, this is the first key with a certain relevance score. And at the end, the concept of self-attention, it's based on a query. So this is what the user is searching for. And the key is a searchable attribute of content. Okay, we're going to search content with respect to certain attributes that are the most relevant to the query among the actual content, okay, that exist into the information system. So the search process, your search query is analyzed, and then we make a matching of content. We calculate relevance score, and finally we rank the result based on their relevance. And at the end, we will identify the most relevant values are returned. So how self-attention actually makes inference? How does this apply to self-attention? We're going to take it step by step. So self-attention is based on trying to identify the relationship between the words. So what we will do, we will take a word. So imagine that you have a sentence like this one. What is the capital of Saudi Arabia? And we expect that the language model will try to predict this word. So how the prediction is going to be made now during the inference? In principle, the transformer will learn from, we assume that this is our value, it's our corpus, and you will make the transformer learn the relationship between every word. For example, if I take capital, what is the relationship of capital with of, the relationship or the relevance of capital with Saudi, capital of with Arabia, with what? So I take a word, I consider this word is the query, and then I will try to calculate the relevance of this word with all other words into the whole value. And we will do that for every word. So I will take it for this one, for this one, for this one, for this one. So in order to do that, starting from a sentence like this, we're going to first of all do the tokenization like we do before, because at the end you will do relevance over tokens, not over words. And we will do the embedding of these tokens. this is the second step, is having this embedding of tokens. We will generate the key, the query, and the value for each of these different tokens. Okay, so from the token Saudi Arabia, if you consider this as a token, or okay, we will calculate the Q of capital, K of capital, V of capital, Q of Saudi, K of Saudi, and V of Saudi. Okay, generate. And the idea here is to calculate what we call an attention map. Okay, how every word is going to relate to any other word in the whole corpus. هذا الأخير, when we train a transformer self-attention module, we will try to capture several relationships, and this is what represent the feature extractor. مثل ما عندنا في convolution neural network, convolution are weights to extract features. Self-attention, it's also another way to extract features, which is the relationship between paragraphs. And in language modeling, we need to understand the semantics, the contextual relationship, the position of the word. Everything is captured through this attention map. Okay, or we call the attention score, which is normalized values between 0 and 1. Okay, and imagine this over a corpus of, I don't know now, for example, if we look at GPT, we talk about 100,000 tokens. So you can imagine matrices of 100,000 tokens by 100,000 tokens replicated over several layers. And you can understand why these models are really huge. Okay. So the self-attention at the end, if I take only one, for example, if I take the different tokens one by one and I calculate the values, at the end is going to extract the most important words that will help me generate the answer. Okay, مثلا الوات والإيز والذي والأوف هذا it's not very relevant to this context. لكن if we look at capital Saudi Arabia, it's likely that it happens in so many other contexts, such that in this context now, if it goes through the self-attention, they are going to have the highest probability. Okay, and now the attention module is going to provide this as a feature, okay, to the feed-forward network later on to help identifying. Okay, so we will have attention scores assigned for every related to this query value, and based on this, the transformer will be able to identify the most important word that will lead it later on to generate the response. Of course, this token will let the transformer understand that this is a question, and based on the learning process, it will be able to generate the next token. So this is the overall landscape of how self-attention works. And at the end, based on the most important tokens that were identified at in the self-attention scores, the model will likely be able to predict that the next token could be Riyadh based on the question. So now I'm going to redo the same cycle, but with all details. This is just an overall picture about how the self-attention works. And this is the summary of the different steps: converting word into vectors, computing query key and value matrices, compute self-attention scores, apply softmax, and compute the final output. Now I understand that you understand a few things, but there are so many things that could be confusing. How do we calculate the key, the query, and the value? How can we make computation? What could be the result? And so on. This is what I try to respond right now. So you can think about every word will have an embedding. So let's assume that we have a three-dimension embedding, very simple. Okay, this is the word representation of what. This is the word representation of is, of the capital. Everyone has a word representation. And now the next step is to define the query key and value. So what we will do, we will start from query matrix, key matrix, and value matrix, which let's assume that they were trained. Of course, in the beginning, they will be completely random, and then with the time, now assume that it was trained, and we get these values into the self-attention module. And afterwards, for every word, we need to calculate its query vector, its key vector, and its value vector. So how to do that? I will take capital as the query. And you have already identified, we have the attention scores or the matrix for the query. So what we will do, we will do the dot product. And the dot product, what information it will carry us? What is the role of dot product in this context? Semantic similarity. صح ولا لا؟ فالكل بنستعمل dot product هنا. This is our query, and we will multiply by the query matrix. So at the end, we will have the query value of, this is the embedding, this is the weight, and this is the Q value of capital. واضح ولا لا؟ Don't precipitate. Let's understand this is the way how we calculate the query value. Let's assume it's simple computation, doesn't have any meaning, just computation. We have weight for the query. This is how we define the attention. It's basically on weights. Everything is weights. Weight for the query, and weight for the key, and weight for the value. It's very simple. I take the embedding, I multiply by every matrix. At the end, I have a query representation of capital, a key representation of capital, and a value representation of capital, and this is what takes us to this table. So it's like I calculated this value, and this value. And I have to do the same for everything else. I will take the embedding of any word multiplied by the weight matrix, and I will find its representation in 3 different spaces. There is a space for query, there is a space for key, and there is a space for value. Why? Because each time the self-attention, how it works, is going to consider every token one time as a key, one time as a query, and also it will be part of the whole value, which is the whole corpus, let's say. Okay, so I'm going to take every word as a query and compare its relevance with all other words in every context. And the context length ولا كل الكلمات كل كلمة it will be a query, and I will calculate relevance score مع كل كلمة الأخرى. واضح ولا؟ والدوت برودكت لما تشمل شنو relevance score؟ هو الدوت برودكت with the query and the key. This is going to give me the similarity between every query, every token with any other token. I will illustrate this, but just try to think about it right now. And what is the difference between dot product and cosine? Why I don't use the cosine similarity here? أما أفضل. Normalization أفضل. صح. But not in this context. If I use normalization, what I'm going to lose? If I use normalized dot product, اللي هو cosine similarity. Cosine similarity is dot product divided by the norm. يعني all the vectors are unit vectors. يعني unit vectors no magnitude. جيد ولا مش جيد؟ إيه جيد ولا مش جيد لو نستعمل cosine similarity؟ ها؟ It's not clear. مو جيد، لماذا مو جيد؟ we need the خاطر لو رخص الماجنتيود خسرت معلومة. فنصبح الآن حتى different magnitude رجعت من نفس الشيء كان من نفس الشيء. فالماجنتيود هنا مهمة. احنا قبل عملنا النورماليزيشن على مسألة الكمبيوتيشن ستابيليتي. حتى هنا تجي المشكلة. لكن فيها حل آخر غير النورماليزيشن في المجال هذا. We will see it. فالآن when we do the dot product we're going to compute the similarity ولا the differences between the word اللي هو relevance at the end both in terms of magnitude and in terms of angle. صح ولا لا؟ This is the dot product. Okay. So الآن فهمنا الفكرة العامة. خلينا نمشي أكثر تفصيل. We start from the word capital. It has the following embedding. What we do? We calculate its query vector. Very simple. Q capital, weight multiplied dot product with the embedding, and at the end I will find Q capital. And I will do the same thing with the key matrix. It's shared. The key matrix will query matrix shared for all. They will have dot product. Every self-attention module will have key matrix, query matrix, and value matrix. And we calculate the value and the key and the value. Okay, now we understand this one. So what we will have at the end? We will do the same for all others. Okay, so this will be the key value for what? The key value for is, the key value for, we will do the same process. I'm at computation for capital. We do the same process. At the end, you will have key values for all the words in the sentence, and you will have values of all the words in the sentence. فذاك هو التيبل الأول اللي احنا عملناه، لكن الآن مفصل. Okay. what I did in this case. طيب علاش ما استعملتش من الأول embedding؟ لماذا حولت من embedding؟ نفس المشكلة، كل space عنده معنى. في space you will consider the word as a query. Another space you will consider the word as a key. And another space هذه كنسميوها projections. هو dot product عنده معنى في الجيومتري اللي هو البروجيكشن. projection on the x axis on the y axis. والبروجيكشن ما تغيرش من نوعية الفيتشرز. هذا هو من الأشياء حتى إذا كان درستوا البي سي اي ولا singular value decomposition. It's basically a transformation from one space to another. That's the whole thing. فالترانسفورميشن in space تغير الريبريزنتيشن لكن ما تغيرش الحقيقة. كما مثلا قلت لكم الآن، إذا كان موقع هنا نقول لك موقع الجي بي اس a certain value، ولا موقع with respect to دكتور محمد 02، ما يغيرش من الشخص الموجود، ما يغيرش من البوزيشن، لكن يغير في وصف البوزيشن لاعتبارات منطقية. Okay. So this is just to make you understand the relation about this concept in linear algebra and how we interpret them into the context of self-attention. So we start from embedding vectors, and we're going to project these embedding vectors into three spaces, because every space will have a certain role, where each token will play the role of a query, will play the role of the key, will play the role of the value. And based on this, if we make all the different combinations, we will find the self-attention score, or the relevance score. And if I have 10 words, how many computations I have to make? How many combinations I have to make? 10 by 10, 100. هذاك علاش عندنا quadratic complexity. الآن لو ناخذوها من معنى مجمل. وهذا أمر من الأشياء النيجاتيف في الترانسفورمر، الكومبلكسيتي اوف كومبيوتيشن. احنا الآن نتوك 10 by 10 لكن we have 100,000 by 100,000. It's a nightmare. Okay, but there are solutions that mitigate this problem. Okay, so these are the different matrix representation. We're going to have matrix representation for every type of token. And everything is based on the concept of dot product we already introduced, but this is kind of a reminder. Okay, so here we're going to capture both the impact of magnitude and the impact of the direction, the magnitude similarity and the direction similarity. So the dot product in this particular context is more important than the cosine similarity, because it will able to have a better feature representation. A magnitude is a feature and the angle is another feature. So we cannot, but we will have the problem of what now? We will have the problem of this dot product can go very high. كيفاش نحلو؟ We will come to it. Okay. So in principle now, I'm going to take word by word. We have calculated all the different key query values for all different words. And now we'll take one by one I will take the capital as a query and calculate the relevance score with all other values. شوف الآن. This is Q capital multiplied by K excluded this word. Okay? This is the key values of كل الورد موجودين في الكونتكست. ما هو عندي what is the capital of Saudi Arabia. نشيل الكابيتال ونخليها في الكويري and I make a dot product with the key. So what is this result here? Why it's called attention score? إيش معناها attention? So attention it's like هي انتباه بالعربية انتباه. Okay? هي بلغة أخرى it's the relevance between this word and all other words. إذا الدوت برودكت كبير مثلا من بين هذه وهذه، شوف مثلا هذه 325 يعني الكلمة هذه عندها علاقة كبيرة جدا بالكلمة هذه. سعودي أرابيا وكابيتال عندهم علاقة ببعض، أرابيا وكابيتال عندهم علاقة ببعض، لكن مثلا وات وإيز وذي علاقة أقل خاطر جاوا في سياقات أخرى in different other context. اللي عملناه مع الكيو كابيتال نعملوه مع الكيو سعودي أرابيا، مع الكيو مش ناخذ كل كلمة attention scores، كل كلمة attention scores، كل كلمة attention scores. ف this is actually the dot product. It measures the similarity in terms of magnitude and direction. لكن عندي الإشكال of these values can go very high. وإذا كان ندخلهم مثل ما هم فيما بعد في الترانسفورمر تصير لي مشكلة الاكسبلودينج gradients و instability و non convergence هذوما الكل. So this is why okay before so we're going to have the attention scores as these values, and this is why in the first transformer paper they tried actually to calculate the scaled self-attention score, and it's the attention score between two words is calculated as the dot product. So here they have chosen a constant, a square root of the key dimension, to divide by this value. And this actually helps to prevent the dot product from growing too large in magnitude. This is the first step to control the exponential increase of the dot product, or the large value of the dot product. هذا يخفف المسألة لكن ما يحلهاش نهائيا. Still, dividing by this value, and it's small, is not going to contribute much into solving this effect. So how to normalize? In this case, we use the softmax function. And the softmax function is going to convert any value into another value between 0 and 1, and the sum of all values is equal to 1. So it's like distribution of probability. كان عندي distribution of numbers, floating number, تصبح distribution. So it's like a projection in another space without changing the feature information. Okay. Okay, so now we have the word, the scaled score, and then we apply the softmax function. فالأخير شاعطيني it's a distribution between 0 and 1. لو نعمل المجموع of all these values is going to sum up to 1. This is the characteristic of softmax function. مثل السيجمويد في الباينري, and this is applied to all these attention scores. This is their sum. So at the end, and this is what we call the attention weights. الآخرين تسميه attention scores. Before the softmax, we call them the attention scores, and after the softmax, we call them the attention weights. And the attention weight, it's going to be kind of proportional or more representative to these values. Okay, نعرف احنا الsoftmax it will put large values close to 1 and small values close to 0. Okay, so it's like scaling the values, normalizing the values between 0 and 1. فالآن مثلا نلقى أنه capital 0.13, Saudi 0.2327, okay, في concentration around these particular words. Okay, and this is just a summary of the previous slides. You start from attention scores, applying softmax, you convert them into attention weights. This is now our feature extractor. Okay, of course, you can think about matrices about the whole dimension, number of tokens, and embedding. So there are multiple dimensions: embedding size, number of tokens, okay, positional embedding. Everything now is integrated into these weights. These weights take into account the words embedding, the position embedding, okay, the relationship between these words. And this relationship, they capture also the position information that we have calculated before from either position encoding or the position embedding. Okay? So now, الآن, using this heat map, we have more tokens that provide focus. الآن لما نوديها الريجريشن ولا الكلاسيفاير خلاص it's like a feature vector this one. Okay? في المفهوم بتاع neural network, dense neural network, convolutional network, it's similar to the feature vector that we get at the end to later on pass it to the classification module to tell us what's happening depending on my task, whether it is classification or regression. So the task here, it can be a regression, which is finding the probability of the potential words, or it can be an embedding vector, like in case of BERT, okay, as representational models. So it depends on how you want to use these attention weights later on for depending on your task that you are interested in. And finally, we compute the final output. Okay, هذه الآن attention weights, it's a feature extractor. Now, what we do, we will make the sum of attention weights multiplied by, هذا مازال ما استخدمناهش. The value contains all the different tokens. Now, this is the third dimension that we didn't use. If I have attention weights multiplied by all the words, I make all the sum, and I will find another embedding vector which represent the context enriched representation of that particular context. It's like magic. Tara, this is very difficult. And I heard Andrew G, he said, I didn't understand this paper from the first time. It's very difficult. I spend a lot of time, you try to always improve your understanding because it's very, very challenging. But it's amazing. It's really one of the most amazing results we have ever seen in artificial intelligence. It's very smart, very clever how we can capture the contextual relationship. Of course, what is happening in transform is much more complex than this kind of intuition, but this is what actually happens in reality in the background. And you can imagine the scale of all tokens, how they map all together in order to provide you this context-enriched representation of the vectors. And now this is what makes the magic of large language model. They are able to do tremendous, amazing applications. Okay, now if you put this into the context, so all of this represent one attention head or one attention module. Okay, so the attention module, it means calculating relevance scores by making the dot product of key and queries. So if I tell you what is this, you tell me this is the result of the dot product between key queries, and then we apply the softmax. And then it applies to the value of the tokens. This is the value matrix. And finally, we get weighted values. We make their sum, and this what represent the context-rich information, which is basically the same as this. This is just a summary of all what we've done into one simple block that we call self-attention module. And you can imagine that in one attention block, we have multiple attention modules. كل واحد, it will make feature extraction. It's like you have several convolutions. Every convolution layer is going to extract certain type of feature. Because we don't know what is these features. احنا الآن we make a simple example to infer what is the relation, but there are so many relationships. مثلا relationship ما بين الجندر, ما بين التايب, الكاتيجوريز, there are different features latent features that the model tried to infer, and not necessarily we don't know even what are these features. So this is more complete, more comprehensive than word2vec, for example, which is a similar semantic relationship between the different words into a very specific context window. Now this is a very large context. Now we have reached 200,000 contexts. Now the newer models like Gemini work at 1 million tokens, 2 million tokens with the new languages. Imagine that 2 million tokens that can be processed into one transformer and generate very fast inference. And recently, 2 days ago, DeepSeek have released a new type of attention. وانا نزلت لينكد ان بوست اظن ارسلته لكم سميته الحاجه ام الاختراع. لما حضروا عليه من الجي بي يوز high quality GPUs, they made a self attention that makes the inference faster even on commodity GPUs. This is going to open the opportunity maybe to develop large language model on small GPUs. So I think the future is going to be really amazing as this technology is becoming more and more public, more and more open, and more affordable regardless of the type of resources that we might need. Okay, this is just a summary of what we've mentioned so far, computing the context-enriched representation. Okay, we have the context vector multiplied, so which is the attention weight multiplied by the value matrix of all values. Okay, and this is going to provide the context vector or a context-enriched representation of our input sentence. So why this matters? It has an efficient matrix operation. Using matrices allow for parallel computation of attention across all words. And the self-attention modules, I'm not going to present it today. Today I want just to focus on the core technology, which is self-attention. In the next lecture, we will focus on the multi-head attention and how it works all together in order to make the inference. Because this is going to extract some features, and we will have multiple other self-attention that will be executed in parallel. This is why we use GPU, so it will be distributed on the GPUs, and then the result will be aggregated together to go into the next layer. Okay, this is just another drawing about the self-attention head. You have positional embedding. You make projection into different spaces. The value space, the key space, the query space. Self-product between the query and the value. You do the scaling. You divide by square root of dimension of the key. Apply the softmax for the normalization of the values. You have here attention weights. Multiply by the values. Dot product. You have a new input. What is this? Is the context-enriched vector representation, which will go to another attention layer. Of course, we will have feed-forward network later on to further process. It's like a classifier. Okay, it's going to take this one and apply a nonlinear activation into this. It will help the learning process. Okay, now we will have a look at the self-attention computation and its complexity. So let's decode what is happening inside this computation. This is the overall equation. It's the softmax of Q multiplied by K dot product divided by the square root of the key dimension multiplied by V. And we have Q is the query matrix, K is the key matrix, and this is their dimension. V, it's the value matrix, and it has a dimension n multiplied by dv. N is the sequence length, number of tokens. dk is the dimension of the keys and the queries. They have the same dimension because we do the dot product. And dv is the dimension of value equal to dk. Okay, and n is the number of tokens here because we will have a representation for every token. So what we will do, we have this first computation, dot product qk. So this is n by n attention score matrix. We divide by dk, so this is just a simple division. It's not, doesn't have any complexity. Applying the softmax, just applying a function. And here we have multiply with it's another dot product, which is also n by n. So this is the analysis of the complexity of the algorithm. QK, it has a complexity of the order n squared multiplied by dk. dk is just a factor, so the exponential is quadratic. The complexity is quadratic. The scale by dk, it's O(n) squared because we have element-wise division for n by n matrix. And apply the softmax, it's O(n) squared also because it will be applied for a matrix n by n. So the overall complexity is n squared, which is quadratic complexity. And this makes a major drawback. And this is why large language model can only be pre-trained on highly sophisticated hardware. الجروك 3 مثلا اللي عمله ايلون ماسك last week, يعني they have built a data center of 200,000 GPUs. And they've made this only in 4 months. It's kind of crazy. And I saw him talking that when they have asked the giant GPU providers on how long they need to do that, to make 200,000 GPU in one data center, they said from 18 months to 24 months. And the guy did it only in 4 months. It's kind of crazy. They did a complete data center, and now they have Grok 3. They mentioned that this is like the most, the smarter generative AI model, but still, I mean, it's comparable to OpenAI, DeepSeek. I didn't see anything like extraordinary. I mean, DeepSeek, the good thing is of DeepSeek is not the accuracy only, but it's the cost. They were able to achieve something similar to OpenAI with much lower cost. But now, if anyone achieves something similar to OpenAI with huge resources, I don't think that this is a milestone. Now, the biggest issue, how can we achieve excellent or highly accurate language models with the lowest possible resources? And this is what the Chinese are excelling at to compete with lower resources. And look now, if we change the sequence length, okay, from 128, 512, 100, 1024 until 16,000, look at the complexity, how it increased exponentially. And now you can imagine that this value becomes 2 million. Imagine that you have 2 million input context size and still able to process. Like Gemini now, it works at 1 million input or context length. And when we say context length, it's not only for the input, by the way. It's the input and the output all together. But some of the programming, some of the large language models, they provide you a maximum input size and the maximum token size. And some of them, they say the overall context size is just one number that you need to manage. Okay, so why does self-attention have quadratic complexity? Every token attend to every other token. So we have n by n. Each token computes attention score with all n tokens, and this create an n by n attention matrix by design. So in the case of BERT 512 embedding size, the attention matrix has 2062 elements per attention head in one attention head. Okay, and if you have 12 attention head, you have 37 million attention score. This is in one attention block. Okay, then if you make multiple blocks, you're going to have much more. So the size of the attention of the self-attention depends on the embedding size, depending on the number of tokens, the context length. Now, if you increase the context length, you can run out of memory. And when we trained the Arabian GPT, we could hardly go beyond 2048 context length. In the beginning, we started initial version with 512, 1024, but with the 8100 GPUs, we couldn't exceed more than 2048. Which is small. I mean, you cannot generate long text with this because of the quadratic complexity problem that we face here. So it's a big problem in terms of memory, as already mentioned. The attention matrix grows as n squared quadratically. The computation also grows as n squared. And this is why there was some proposal techniques to make the attention more efficient. So this proposal, the sparse attention and the lean former, linear attention, their objective is to reduce the complexity below n squared. So what does it do, the sparse attention? Instead of attending all tokens with all other tokens, they try to make sparse attention select only subset of relevant tokens. مثلا في عاوز نقعد نعمل attention what و ease لا مثلا I try to select capital مع Saudi Arabia and skip some other attentions. Okay, so there is a way on to choose the relevant token and this reduce unnecessary computation. فهذا من الآن they try to improve computation wise. ثم اللي حبوا يعملوا improve على memory wise. So different ways on how to improve. لأن عندي two bottlenecks. عندي bottlenecks in terms of computation, another bottlenecks in terms of memory. And there are different variations. These are just some technical information about techniques for sparse attention. They were able to reduce sparse attention from n square connections into k multiplied by n connections, which k is the window size. Okay, so k it's a value below n that tells which region, okay, instead of having n by n, okay, for example, each token is going to attend to a certain region of tokens, and some of the regions will be skipped. And there are different ways on how to implement this strategy. The linear attention, it reduced from on squared to on by making a projection, compress them into smaller space with dimensionality reduction. هذا كان بيستعمل PCA, going from one space to another, feature reduction. Okay, it's applying of dimensionality reduction technique to reduce the space. Dimensionality reduction is just to multiply with dot product into another into another space, so we can compress this space into this one, and then we attend all of them together. So this will reduce the complexity of computation from on squared to on. There is performer and reformer, reducing the attention complexity without sacrificing performance. So here, instead of computing the softmax of Q of the dot product explicitly, the performer approximated using kernel functions, allowing for linear time computation. So instead of making the exact computation of this, they do an approximation. في بعض techniques approximation, you can get an estimated value at a reduced cost. Okay? طبعا مثلا complex function, مثلا لما نستعمل Taylor series, any complex function becomes just a sum, okay, of elements. There are techniques of approximation that can reduce. فشفتوا الآن different approaches on how to overcome the computation complexity with the memory complexity by making approximation, by skipping some of the connections. Okay, of course this might, it would have an impact on accuracy, like with the whole large corpus of information there will be a convergence to a good state. Okay, the reformer replaces the standard dot product attention with locality sensitive hashing, making retrieval faster. Okay, if you have the standard dot product for semantic similarity and relevance, standard hashing. Well, hashing is another technique also to retrieve, like indexing, faster retrieving by only computing attention between similar items. Maybe one of the most famous techniques now that is currently used, whole flash attention, and the objective is to optimize GPU memory for faster attention. So every technique has its own purpose. Okay, and you can think about this one as, imagine that you student want to take note during the class, and the student has a small desk which is the fast memory. For example, you put your notes onto the fast desk, ولا خليها مثلا في الباك في الحقيبة مثلا. طبعا this is a slow memory. If you write a lot of notes, okay, if you put it on your desk, it's fast. If you put it in the backpack, it will take you time to put it there and take it back and so on. So this is basically what flash attention try to do. And the standard attention, it just keep going to the slow memory each time. So the idea here is not to be different like other techniques have done. Try to work smarter. So we keep the same computation, no change into the mathematics. Okay, no mathematics change, but we try to improve the information flow between the memory. الآن مثلا in memory flow computation, in standard attention, the KQV, they work in the DRAM, which is the slow memory, and then in the fast memory SRAM to calculate the attention scores, and then we have computation units. For flash attention, they try to do everything into the same memory. So like having try to optimize the flow of data between the memory of the CPU and the memory of the GPU. لأنه transfer of data between two different CPUs depends حتى على الباسز اللي ما بين two type of memories. هذا يأثر كثير في ال computation speed. Okay, this is a more technical slide. The other one is just to give some intuitions. Now, this is how it works for the computation. First of all, we have the standard attention load, the QKV from the DRAM, and then we compute the dot product, and then we store it to the DRAM, and then load S from the DRAM, and then compute the softmax function, and then store P to the DRAM. So you can see how many input and output from and to the memory it happens in the standard attention. In the flash attention, it loads all the blocks, store it in the SRAM cache, because the cache is faster, compute the softmax PV in one pass, accumulate partial result in the SRAM, and write the final output to the DRAM. So we have only one writing into the DRAM, the slow memory, whereas here there is a lot of writing back and forth. So it's basically an optimization on how the self-attention is computed by the GPU. والآن الفكرة بتاع الديب سيك أنهم they try to reduce latent vector space attention scores. They reduce it from one space to a smaller vector, and this makes them able to accommodate with longer context length with a smaller computation requirement. لأنه الاتنشن سكورز أخذوا dimension أقل. فإتس basically a flash attention with dimensionality reduction بالنسبة للتكنيك اللي عملوها الديب سيك. So this is the performance benefits and application. In standard attention it's ON square. In flash attention it's still ON square, but here the reduction is more into the memory space. Okay. A new technique of deep seek, it optimizes both of them. So we optimize the memory and also the complexity of computation. This is just a summary table that compare between all the different optimization techniques: sparse attention, linear attention, performer, reformer, and flash attention. Okay, what is the time now? Yeah, this is the last part, but I'm going to stop here today. We have had a lot of information, and we will continue the remaining part next time, inshallah. Okay, everything is clear? Okay, so I will send you an assignment to do at home to review this part, and inshallah ممكن we'll continue tomorrow. المفروض على الساعة 5. إذا جاني ظرف أني تأخرت هنا I couldn't reach earlier, I will let you know at least 2 hours in advance. Okay, الله يبارك فيك. الأساينمنت تو نزلوا بكرة.